So you're in Iowa City right now. Hopefully you've thought about water quality a little bit. How many of you feel like Iowa's water quality is better today than it was 100 years ago? Anybody feel like it's better? No? What if I said 50 years ago? Is water quality today better than it was 50 years ago? Okay, I'm getting a few people saying yes. What about 10 years ago? Are we making some progress? Yeah? All right. So what I want to talk about is one of the thorniest issues that we've had in Iowa, which is the problem with nitrogen, and specifically nitrate, which is a form of nitrogen. And I'm not going to answer the question that I asked you right now. Hopefully we can get into some policy questions with that and kind of address where we're going in the state. But I'm really going to try and talk about sort of setting the stage for you of Iowa's water quality and specifically what's going on with nitrogen. So why is nitrogen important? How did we get to the current situation that we're in right now? And is there anything that we can do about it? Or are we just sort of lost and we can't actually do anything about water quality? Starting with why is nitrogen important? And I apologize for a big diagram late in the evening here. But it's really important we start talking about nitrogen in Iowa, especially nitrogen in water, to start with the understanding that nitrogen is a natural element in Iowa. Nitrogen gas occurs in the atmosphere, completely natural, right? So how could this be a problem? Well, if you look at the cycle, what happens is we have things like ammonia fertilizer that's applied to crop ground so that crops can actually start to take up some of that nitrogen, because nitrogen is an essential element for plant growth. So we have to make that nitrogen in the gas available to plants. If it's cropland, we do it through applying fertilizer, usually in some form of ammonium. That starts to convert in the ground. And so ammonia will very quickly start to convert to something called nitrate. Nitrate then is very water soluble, which means it dissolves easily and moves through the ground into streams and creeks and things like that. So we've got this cycling of nitrogen that's constantly happening from the atmosphere to the ground, to the plants, back to the ground, back out to the stream. And that cycling, again, is something that we have to just sort of take as granted that that's going to happen. So why is nitrate important for you, other than this cycling is occurring? Well, nitrate, excessive nitrate, can have a lot of repercussions. One is, if we have a lot of nitrate in drinking water, we can have something called blue baby syndrome. And essentially what that means is that excessive nitrate in the gut of a small child can actually interfere with the oxygen uptake in that child. And they get sort of a blue color. And obviously that's going to be really challenging for that child to survive if you don't have enough oxygen in your blood. So that's a condition that's very rare anymore, but something that's very concerning to people, obviously. And as a result, we've set a drinking water standard of 10 milligrams per liter to make sure that if we don't go over that 10, we're not likely to have that blue baby syndrome. The problem is that's a really relatively rare thing that occurs in the country. And more likely, some of the issues that we have are things that are lesser known, but are probably more concerning long-term, things like cancer risk. And we're starting to see the linkage of nitrate in drinking water, streams, creeks, and groundwater being linked with stomach cancers, with non-Hodgkin's lymphoma, with a number of cancers, thyroid cancer. And so we're starting to see that that picture of cancer risk is greater than maybe even this blue baby syndrome. And again, if we're starting to look at where that cancer risk occurs, it may be at levels much below the current drinking water standard of 10. It may be more at the 2 to 3 to 4 parts per million of nitrate. So we have a drinking water standard we're trying to meet, but we know that there's other human impacts. And I refer you to a website. On campus we have a whole group that's looking at health effects of environmental contamination, and they've got a lot of research that you could take a look at there. And then we also have adverse ecological impacts. We tend to be very human-oriented because we're humans, but we also want to make sure that the environment in general is healthy, and excess levels of nutrients, particularly phosphorus and nitrate, can have problems in the environment. One of the most well-known problems is the Gulf of Mexico hypoxia. And this is an image from the Gulf of Mexico from 2004. The red shows you the extent of water that has very low oxygen levels, less than 2 milligrams per liter. If we get below 2 milligrams per liter of oxygen in the water, essentially things that need to have oxygen in that water can't survive. So they either die or they migrate out of that area. So you can see the huge area around the Gulf of Mexico that starts to have this anoxic or hypoxic water. And it's all set up by the freshwater system, the Mississippi River, delivering high levels of nutrients that then the plants, the algae take advantage of, grow abundantly, and then when those plants die, the bacteria consume not only the plant material, but oxygen as they start to break down that plant material. And so this phenomena that we've known about for a long time is becoming increasingly concerning to policymakers, because if you're a fisherman, you don't want to have low oxygen levels. That might be a problem for your fish population that you're trying to harvest. If you're a shellfish person in particular, the shrimp may be having problems, as well as a number of other organisms that are really deeply impacted by this hypoxic area in the Gulf of Mexico. And again, you can go to this Gulf of Mexico hypoxia webpage and you can see how that zone varies from year to year to year. But it has gotten much larger than it was estimated to be even 30 years ago. So why is that important to us here in Iowa? Well, if you take a look at these two maps, on the left we have the yield of nitrate, which is one of the two most important elements for that hypoxic zone, nitrate and phosphorus. So if you look at the yield, you can see that the deeper blue color is where we have higher yields of nitrate coming from the watershed, coming from the ground in that area. So obviously, if you take a look at this map, you can see that Iowa is a very high producer for that nitrate that's making it down to the Gulf of Mexico. We're number one in hogs, beans, corn, and nitrate, right? And why is that so high for us here in Iowa? Well, if you take a look at the second map there on the right, you can see the amount of cropland that exists in Iowa being a very important driver for the amount of nitrate that we're producing in the watershed, or in the state. Okay, so that's from a regional scale. Why is nitrate important to you? Because it's a big driver for a Gulf of Mexico problem that is of national importance. Well, what if you're sitting in a small town in Iowa? Are you concerned about the hypoxic zone in the Gulf of Mexico? Maybe, maybe not. So let's bring it home a little bit. These are data from our ambient monitoring sites, which are essentially streams that we monitor, about 90 streams that we monitor around the state on a monthly basis. And essentially, these are all the data for each month, sort of ordered from highest value to lowest value. And so the box tells you some amount of spread of the data. For example, these dots at the top are the outlier or very high values. This top line, 90% of the values would fall below that line. The top of the box, 75% of the values would fall below that. The middle box is 50% of the values. So if you take a look at this, and I start off by saying, we're starting to understand the cancer risk with nitrate a lot better, and we're starting to think that that cancer risk really starts to occur at about 2 to 4 milligrams per liter of nitrate. If you look at our stream levels and you said, well, blue baby syndrome occurs at 10, or the 10 is the drinking water standard, you might come away with the assumption that while we do violate that in streams in Iowa periodically, we don't do it that often. Although you notice that some of the sites are 3 times that level during certain times of the year. But if you look at that lower value for cancer risk, you start to see that the majority of our samples violate that 2 to 4 milligrams per liter. So 75% of the time, we're well above or above that 2 milligrams per liter, 3 milligrams per liter of nitrate. So then why is it important to you? Well, it's important for the ecology, but it's also important for you living here in Iowa. This shows you a map of export of stream loads for nitrate, and again, you see that it's happening throughout the state. There is no particular area that is really devoid of nitrate, so it is a statewide issue for us. And again, much like the Gulf of Mexico issue, local water bodies like reservoirs and lakes start to have that same kind of hypoxic problem. Have you been in reservoirs or lakes around Iowa in the summertime and you see that really greenish tinge to the water? Do you ever not see a greenish tinge? Pretty rare. It's either brown or green in Iowa. And again, the reason for that is the very high levels of nutrients that are being washed down those streams and entering into those lakes and reservoirs where they intercept that stream. So that the hypoxic zone not only occurs in the Gulf of Mexico, but right here in Iowa. It occurs at the Coralville Reservoir in places. It occurs in Lake McBride at places. So that we have these aquatic issues locally as well as nationally that we need to be concerned about. And this just shows you areas, these are what we call impaired waters. They're waters that are not meeting their intended use. So for a lake, the intended use would be to be able to swim there, to be able to fish there, and possibly drink there. So we can see that we have, in 2010, 51 of our lakes that are impaired for high levels of algae, that excessive algae growth that then leads to hypoxic conditions. So again, we've got the same sort of problem here at home that we have also in other parts of the country. So why is nitrate such a big issue in Iowa? What is unique to Iowa that puts that bullseye right on our state in such a big way? Well, to talk about that, we have to think about the history of Iowa going back. And this is where, remember I started talking about, well, what was the water quality like 100 years ago? Let's back it up to 300 years ago. What did the state of Iowa look like if you were coming across as a European settler? Did it look like it does today? Not hardly, right? So this map on the left shows you essentially what the ecology looked like. We were mostly in tall grass prairie in the state of Iowa, extensive tall grass prairie up and down the Midwest. The map on the right shows you what we call hydric soils. And a hydric soil is just something that's a wet soil. It held water most of the time. And if you look at this map where you've got these really dark blue areas, those were extremely hydric soils, or basically wetland soils. And so when you look at the map of Iowa, you notice that a huge chunk of the state had very, very predominantly wetland areas. Even though it was prairie, it was maybe a wet prairie, standing water in the prairie as well as in depressions. So the state was really a very wet area. It had a lot of water sitting around. The soils really developed to hold the nutrients that the prairie was developing. Any rainfall that fell in the prairie was first intercepted by the prairie leaves and then slowly worked its way down to the ground if it didn't evaporate right off the prairie. And so what happened is we had a hydrology that was very dominated by groundwater. The water moved off the land, basically through the land very slowly and mostly in the groundwater portion of the hydrology. So if we take a look at the hydrologic cycle in Iowa, this is kind of a cross-section. Most of the water in Iowa used to move essentially underground or very slowly at the surface of the ground. We had some defined streams, but actually many fewer defined streams then than we do today. We've added to the stream miles by ditching and adding areas of stream. So we had a very slow groundwater system. And the big thing for nitrate is by having that water at the land surface, that ground being saturated, it didn't really allow for the nitrate to be formed in a dry part of the soil. If you go back to that first graph that I showed you, nitrate forms in the presence of oxygen. If we have water sitting throughout that land, we're not producing that nitrate. It's essentially locked up in those soils. So we essentially had the nitrate there, we had nitrogen there, but it wasn't really able to be formed in a nitrate and moving out of the system. So the problem with that, though, is when you come in as a settler and you want to grow corn or soybeans or some kind of crop in that landscape, it's too wet to plant a crop. You can't plant a crop in a wetland. You have to draw the water down so that you actually dry the soils out so you can actually plant something, right? If you overwater your house plants, they're going to die. It's the same sort of philosophy. So to actually make this ground good for crop ground, we had to draw the water down. We had to basically aerate the soil, get oxygen into the soil. And the way that we do that is through tile drainage. So here's a kind of a cross-section of how that works. And essentially, if you've been driving around the state, you see right now there are linear patterns on the croplands. What they're doing is they're putting in additional tile. And those croplands have this tile buried about 6 feet down. Sometimes they have surface pipes, sometimes not. And essentially what that does is it draws the water into the pipe and then out to a stream. So that you're essentially drying this part of the soil out so you can have a crop in there. If you didn't draw that water down, it would be too wet to grow anything here and you'd be unable to have your crop. So the tiles have been extensively put across the state to the tune of about 1 million miles of tile have been installed in the state of Iowa, which is about 7 or 8 times the amount of road network that we have in the state. So you think about all the gravel roads, all the secondary roads we have in Iowa, multiply that by 8. That's the underground tile network that is drawing water down and out to a stream as quickly as possible. And again, the nitrate is forming in that soil layer so that when it rains, all that water that infiltrates to the tile line catches the nitrate and moves it out with the tile. So we've got a great production of nitrate now and a great delivery system to our stream by adding that tile modification. So how has this hydrologic modification impacted Iowa specifically? Have to talk a little bit about how water is moving in Iowa from a hydrograph point of view. And a hydrograph is simply just a graph of how much water is moving in the system. So if we look at through time, how many days, how much water is moving in that system. You could sort of roughly think about the Iowa River, how much of the water is moving in the Iowa River at any particular time. As the water gets higher in the stream, we're going to have a higher hydrograph. As that water level drops, we're going to have a lower amount of water in our hydrograph. And the reason that's important for you is because there's two main components to a hydrograph. That which it comes in the base flow, which is essentially the groundwater contribution of water to the stream all the time. That base flow is what's driving the Iowa River right now. If it hasn't rained in weeks, the Iowa River doesn't go dry because groundwater continues to supply water on a regular basis. But if it rains heavy tonight, that river will jump up. What happens when it jumps up is a lot of that is what we call storm flow. That's the water that hits the ground and shoots off the top of the ground into the stream very rapidly. And so we have two components that are delivering water from two different parts of the system. One that's providing that high level of nitrate-laden water through the ground system, through the tile system, and one that's coming directly over ground that doesn't have as much of that high nitrate water. So let's take an example. I know that's kind of a big theory. Let's make it a little bit more real. Let's take a look at the Raccoon River as an example. The Raccoon River is important because it provides a significant amount of drinking water to the city of Des Moines. They have had perennial nitrate problems in the city of Des Moines, not meeting the drinking water standard. 80% of the land use in that area is agricultural, and they have long-term stream records, which is good for us. A lot of graphs here, but the base take-home message here is that when we look at the last 100 years of records on the Raccoon, we see two very interesting things happening. One is that the total amount of flow or water in that stream is increasing through time. So we have more water overall getting into the stream. The other part of that is we have more of that water coming in that base flow, nitrate-laden contribution. And again, a lot of that's really being driven by the tiling that's occurring, taking that base flow and making it a little bit more rapid in terms of how fast it's getting to the stream. So we've got more water overall and more nitrate-laden water getting to our streams, which again gets to the lake, which gets to the Gulf of Mexico, which causes some challenges for us. To give you a more specific look at that in more detail, we have continuous nitrate monitors that look at nitrate in the Raccoon every 15 minutes. And so if we take a look at this diagram, it really dissects for us what's happening with where the water is coming in the system. So for example, this blue line is how much water is in the stream. And you can see we get rainfall events, a big peak. We had a huge peak here in 2008. Flood, anyone remember? Yeah, 2008 flood right there. And we were fortunate to have these nitrate sensors looking at nitrate during that flood peak. And what you notice is that every time we get a big increase in storm flow, the nitrate drops. So you see a peak here, you see a decrease there. You see a peak here, you see a decrease in the nitrate. So essentially we can really start to dissect where the water is coming from and whether it has high levels of nitrate or not. And the reason that's important is if we're going to fix the nitrate problem, we're going to fix the Gulf of Mexico, we have to know where the water's coming. We have to understand how the water is getting to the stream, because otherwise we can suggest solutions that aren't going to ever fix the issue. We have to make sure we're looking at the right component of the water. Trying to address nitrate problems in Iowa by fixing urban stormwater will not get you anywhere close to the problem, because such a small portion of the urban stormwater has nitrate in it. So we have to think about where is that source coming from. And again, just another example, this is looking at the Iowa River. These different dots are tile lines that were sampled. And again, you notice that the tile lines are running anywhere from 25 to 35 milligrams per liter of nitrate. Very, very, very high levels. So again, when we start thinking about solutions for nitrate, we have to think about how do we address the tile flow, considering that we have 1 million miles of tile flow. Where do we start with trying to address each and every one of those outlets? This is a very small segment of stream. Look at how many places those tiles are coming out. How do we address each and every one of those tiles coming out into that stream? One thing I will say, though, is that the impact of altered hydrology is not a uniform thing across the state of Iowa. We do see regional impacts in Iowa that are a little bit different. In particular, the southern part of the state where we are is not quite as bad as the northern part of the state, where that blue hydric soil area was the biggest. Those hydric soils had to be intensively tiled in order to have good crop ground. In southern Iowa, we don't have the same level of tiling because we don't have the wetlands that we had up north. So we can look at that through a mapping convention called ecoregions, which is basically looking at the state and breaking the state down into regions that are similar with respect to how the water is coming into the stream, what kind of ecology would normally be there, what's the topography of the state. So this middle area, which had a lot of those wetlands, is called the Des Moines Lobe, and it was last glaciated about 13,000 years ago. Southern Iowa, in comparison, was last glaciated anywhere from 250,000 to 500,000 years ago. And so this part of the state has a lot more rolling topography. If you drive I-80, you can definitely tell when you're off the Des Moines Lobe because it's no longer flat. It's very up and down. When you're on the I-80 with the trucks and they're zooming up and down the hills, you can tell that you're on that southern drift plain. Northeast Iowa tends not to have a lot of soil on top of the bedrock, so that anything that's applied to the bedrock in this area or to the soil in this area goes directly into the groundwater and is delivered to streams. It's a very vulnerable landscape. And over here we have, for example, the Luss Hills, which are, again, highly erodible. They tend to erode. The sediment tends to get into the stream, but tends not to have as high of problems with nitrate. And we could take a look at the base flow changes relative to those different ecological regions. So again, something like the Grand Fork of the Thomas River, you can see that the base flow component has increased, but it's only gone to about 30%. Whereas something like the Turkey, the Winnebago, and the Raccoon, we're up closer to 50 to 60% of the stream is delivering in that base flow component. So if we start to think about where we need to focus our effort, and if we look at this map, what parts of the state have the highest levels of nitrate day in, day out, year after year? The focus area really becomes this north-central part of the state where we have median levels of nitrate that are, again, above the drinking water standard and approaching 15 milligrams per liter. Southern Iowa, we're not going to get as much bang for our buck because the levels just don't start off as high because we don't have that groundwater-dominated system. So we have to think about targeting where we're going to go with our practices to get the most good out of those dollars. I have to throw this slide in because one of the things that people ask oftentimes is, you know, hasn't Iowa always been a really high nitrate-laden stream state? Isn't this always the way it's been? And I started off by asking you about 100 years ago. I don't quite get back 100 years, but, well, I guess I do, 1905. If you take a look at what the Cedar River and the Des Moines River were doing 100 years ago, we were well below 1 milligram per liter for nitrate in those rivers. Now, in 2006 is the last data point that I have here, we're well over 6 as an average. So you can see that we've continued to go up, 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 up with our nitrate levels. However, we do know that the background or the natural condition was much lower. And so we shouldn't probably start by having the assumption that we always had high nitrate and we can't go backward. We did have low nitrate levels to start with, but how do we start to take into consideration that we do have cropland now, we have tile lines now? How do we start to get back some of that processing of nitrate and get those levels back in line with what we saw in the 1900s or even the 1940s? There's a couple of different things we can do with nitrate control. You were already hearing a little bit about some of the Clean Water Act provisions. The Clean Water Act is a great piece of legislation, but it's got a few issues when we start to look at nitrate. First of all, hopefully you all know about point source and non-point source pollution. Point source being essentially it's coming from a defined point, usually a city wastewater treatment system or stormwater point. That's regulated. The DNR can come in and tell you how much you can deliver out of that point. I can say you cannot exceed this level of ammonia coming out of your pipe, and if you do, there's going to be penalties for that. On the other hand, we've got non-point source, which is coming from agriculture, and those tile lines are considered non-point source pollution, even though they come from a pipe. Under the Clean Water Act, we are not allowed currently to do anything in terms of regulation about saying you have to drop the levels coming out of those tiles. Everything we have to do is voluntary. We have to ask producers to think about things that they can do on their watershed, on their landscape, to reduce their nitrogen levels. We cannot enforce a regulatory limit at this point. So we've been successful in the point source world of reducing ammonia, for example, coming out of wastewater treatment plants. We've been successful because we have the ammonia and we convert it to nitrate and then deliver it. So ammonia is toxic, nitrate isn't directly toxic, so we are actually converting our wastewater treatment system ammonia to nitrate and delivering it that way. But again, we need to think about voluntary approaches for the Clean Water Act, non-point sources in the agricultural fields. There's three sort of main ways that we're going to talk about that we can do that. One is looking at source control. One is looking at treatment on the site and treatment off the site. So essentially source control, the first thing people go to, and you see it in the hypoxia reports, is we should just use less fertilizer. If we just use less fertilizer, the nitrogen levels will come down accordingly and problem solved. The problem is that all the modeling that's been done suggests that reduction of fertilizer alone won't get us there, partly because just by plowing up the landscape, by aerating that land, the natural organic matter is releasing nitrate as well. So we're getting nitrate forming just by tilling that land and putting a crop in. We can reduce fertilizer use, but it's not going to be the only solution to getting to levels that are back to 1905 or 1940 levels. And you can see that our nitrogen use has leveled off a bit. We tend to bounce between 120 and 140 kilograms of nitrogen per hectare. But we can try and reduce those levels, but if we're going to reach a 40% or a 50% goal of reduction, source control alone is not likely to do it. The other part of source control that we found out is that in Iowa we have an awful lot of cows, an awful lot of pigs, and an awful lot of chickens. The manure from those animals are applied to the ground as nutrients. What we found is that very few people take credit for those nutrients. They put them on knowing that they're going to provide nutrients to their crop, but because the levels of nutrients from manure are very unreliable, you have a huge range in phosphorus and nitrogen that you can get out of manure. A lot of producers were just sort of assuming that that level was zero and adding what they were required or what they wanted to put on their crop in the synthetic fertilizer and then putting manure on top of that and not taking that credit. So one of the things we're working on is trying to look at what is the actual balance of your crop that you need for fertilizer use. And can you balance it with manure inputs as well as fertilizer inputs and not over-apply? Because when you over-apply, that's just essentially going right down the creek. We can also think about treatment on site. So if we can't get there with just reducing fertilizer, what can we do on site? One of the new innovative things that we're looking at is cover crops. When the corn is harvested in September or October, that land sits basically dormant until you start planting in April or May. During that time, all the nutrients in the soil continue to leach out and be delivered with every rainstorm. And if you think about a year like this year, where we had rains in January and February, every time it rained, high nitrate level water was moving down into the stream. There was nothing to take up that nutrient. If we plant a cover crop, these cover crops can actually be growing as the corn is dying. You can plant it in between your corn with an aerial application, seeding the rye into the corn as it's dying. And then it continues to take up nitrate as the corn is going into senescence. And you have that cover crop sitting, taking up nutrients essentially the entire fall, winter, and early spring before you start planting again. And these are a couple of pictures. On the right, this is what it looks like when you're just getting ready to burn off that cover crop in the spring to plant the corn again. And this shows you some soybean seedlings cutting up between the cover crop. A very effective way of taking up nutrients, and studies are showing, for example, how much reduction you get in tile line nitrate levels just by having a corn crop or having a cover crop, up to a 50% reduction in some cases of the nitrate being delivered just by having that cover crop sitting there. Huge. Other things we can do for treatment on site, I talked about the tile lines always sort of flowing that water to the stream. They're gravity fed, they're just doing it all the time. We can actually start to manage that water in a different way. If we hold that tile water back at times that we don't want to be planting or we don't want that corn crop to be drowned out, if we back that water up, essentially we're allowing that soil to start to denitrify and lock the nutrients back into the soil. If we saturate the soil, we're basically replicating the conditions in Iowa 300 years ago. So if we manage our tile water with stoppers by backing that water up, we're going to be pretty effective at locking those nutrients up. And again, some research suggesting that 30 to 80% of the losses could be avoided by using drainage management water in a different way. Lastly, we could treat that high nitrate water off-site. So instead of having my cornfield do it or having my tile line do the work, I can ask someone else to take on that responsibility. In Iowa, that's being done in sort of two main ways. One way is through these crepe wetlands. Essentially, my tile is going to be intercepting water that's got high levels of nitrate in a wetland system. And again, that wetland's going to do a lot of denitrification and drop those nitrogen levels down pretty significantly. In Calhoun County, for example, we could take a look at putting back a number of wetlands that are going to treat essentially the whole county. So, there's a number of wetlands that could be sort of re-established in the county to really address the high levels of nitrate. The problem with this is that you're taking maybe 10% of the watershed to put back into wetlands. And right now, corn prices are so high, no one wants to take a single speck of land out of production. It's just not a very attractive thing to do. The other part of that is when you look at the cost. So for example, if you're trying to address through best management practice edge of field losses, through a number of best management practices like, again, reduction in fertilizer use or cover crops, you may be paying 88 cents up to $3. Look at the price of putting in a wetland. $6, $8 to put in a wetland versus pennies on the dollar. So it's a society issue about, do we want to spend a lot more money to put in wetlands that are effective at reducing nitrate, or do we want to do things on the cropland itself to reduce those levels? And with that, I'm going to close and toss this over to Craig.
Okay, so I'm Craig, and I'm in my 20th year at the university. I'm in the College of Engineering. I'm trained as a chemist and an environmental engineer. And Mary Skopek's one of my heroes, and she's awesome. And so I'm tickled to be with you here tonight. As you can tell, I prefer to be more engaging than lecture style as best I can, so I'll try to reflect that in what I present. One of the things I want to do is follow up on Mary's work on her presentation with respect to the nitrogen cycle. And I'm going to talk about how freshwater mussels impact that cycle. So in a nutshell, we're going to talk about mussels and how they eat, puke, and poop. All right? And so everyone read that book? As a child, my kids are older now, but I had a book called Everyone Poops. Yeah. Everyone heard, sweet book, very classic book. Well, mussels poop as well. They also puke, and they do these things, and they eat as well, and they do it daily, just like you and I. So mussels and humans aren't that different. And it turns out, just like us, mussels eat things that have nitrogen in it. And when they eat things that have nitrogen in it, it's typically in a more oxidized form of nitrogen. And then when they poop it out, just like you and I, they poop it out in a reduced form of nitrogen, so like an ammonia. They pee things out too, technically, also in reduced forms of nitrogen. So mussels have the ability to have a huge impact on the nitrogen cycle in these rivers and streams that Mary has kind of told you about. So one of the things that we could think about from an engineered standpoint, if the nitrate already makes its way into the river, boy, now what do we do? It'd be great to have some mitigation effects engineered systems there as well. In the Iowa River and the Mississippi River and other places, as Carl Sagan would say, there used to be billions and billions of mussels in those waterways. And now there are millions and millions of mussels, many, many, many mussels around. An adult mussel might be 60 years old, and that adult mussel might filter 25 liters of water a day. And so what I mean by filter is the way they eat is they have a siphon, and they can suck water in, and in that water there'll be particulates like phytoplankton. There'll be soil and other things that they don't want to eat. But that phytoplankton, or algae, contains nitrogen, right? So phytoplankton is a living organism. It needs nutrients to grow. It grows on a diurnal cycle, up and down, as sunlight comes and goes. Mussels will effectively suck that in through their siphon. They can discriminate against good food and bad food. Mussels do not like to eat dirt. We don't either. They like to eat plants, and so they can discriminate, and that's why mussels puke. They puke out the stuff they don't want to eat, and then they discriminate and put in the things they do want to eat into their digestive system. After they digest, they essentially generate feces, and those things are in reduced forms. Another interesting thing about mussels is that they live at the water-sediment interface. They're called ecosystems engineers many times, and so they live in a very unique place where they can pull things that are in the water column, right? Pull those things out of the water column and then deposit it in what's called the benthic zone of a river, or the bed of a river, into the mud, into the sediment. And so they can literally take it from one compartment, the water compartment, and move it into a stationary compartment in that sediment. Is that going to make sense? You guys see how that would work? So that's where they live. They actually burrow down in there. If you put a mussel into a lab setting where you can see what they do, you lay them on top. After a while, they'll dig in, and all you can see is just their little siphon up above the water. And then they're pulling in things as they need it. When they're threatened or they want to move around or do something or find new food, they have this large muscular foot. If you guys watch SpongeBob, those mussels, those big clams are typically on their side, and they open up like this. It looks like a tongue. Mussels actually orient themselves like this with their gape vertical, and they open up like that. And what is like a tongue in that giant clam in SpongeBob is actually a foot. And that foot comes out, and it can move itself. It can rock back and forth and burrow. It can actually move as well. It'll move several feet each year as water levels go up and down. In fact, there was a giant mussel kind of recovery effort, a movement effort, when they were doing some work on the outflow of the Coralville Reservoir earlier. Actually late last year. They dropped the levels of the Iowa River down really, really low. And some of these mussels then became exposed, and so a whole bunch of people went out there in waders and tried to move them into deeper water, because they can't move quickly. They're not exactly sprinters. They're really interesting, though, because they're kind of an indicator species of all things interesting, I think, with respect to water quality. In particular, how it impacts with respect to nitrogen, that's fine. But they're also kind of, their giant muscular foot is essentially fatty tissue. And just like you and I, all sorts of environmental contaminants of concern accumulate there. So they're like these giant samplers, environmental samplers, that integrate what they kind of see over time. And we can actually go and harvest mussels and unfortunately, sacrifice them, but extract the things out of them, extract their tissues, and get kind of an overall picture of what's been going on these long time scales, decades ago, to see what these mussels have been exposed to. And so that's a little bit about some of the, I guess in a nutshell, what we're doing. One of the mussels we have in our laboratory setup that I'll show you here in a little bit is pregnant. She's essentially displaying her attractive organs. It's pretty fascinating to see it. The mussels require a fish host to reproduce. And so this mussel has got some attractive organs that look like little minnows, or little attractive organisms that a larger fish will think is a smaller fish to come eat. And then as that larger fish approaches the mussel, she'll inject her larvae into the fish's mouth. And then the juvenile, the larvae, the eggs, essentially will get trapped on the gills of that host fish. The juvenile mussels will start to grow and use the fish as kind of a nutrient source and an energy source. Also a way to kind of move and relocate. Then when the juvenile mussels get large enough, they'll fall off the gills and then turn, and grow into an adult mussel. again, some of these mussels can be, 60, 70 years old in the end. So I'm really, I'd love to, and by the way, my research lab is just over here at the University of Iowa Drinking Water Treatment Plant. We actually pull in Iowa River water into our system and run that through there continuously, and we've got mussels in there doing all sorts of interesting things. So if any of you are interested and want to see that stuff live, I'd be happy to take you over to my lab and show you anything you want to know about freshwater mussels. We could do the history of freshwater mussels. We could do the ergonomics of freshwater mussels, physiology of freshwater mussels. We could do they know a little bit about politics. I'm trying to cater to your majors as best I can. But come on over and check it out if you want. They're pretty fascinating, and I can, I'd love to share. So I'm going to go over this research of my most senior research student. His name is Jeremy Brill. He's getting his PhD with me. The title of his topic is Quantifying Freshwater Mussel Diurnal Nitrogen Dynamics. Diurnal meaning daily. That goes up and down daily. I think we already got a decent, we did get a great introduction by Mary on the whole idea of Gulf hypoxia, because one of the things I'm interested in is, can these mussels perform an ecosystem service? Can we get enough of them out there in the Mississippi River or the Iowa River, or rejuvenate their habitat? What's the cost-benefit ratio of doing mussel habitat versus wetland habitat for reducing nitrogen and removing that before it gets down to the Gulf of Mexico? So my research is really in the same context of what Mary has already described for you, to try to mitigate Gulf of Mexico hypoxia. One of the things that we did pretty early on, this data here up at the top that's kind of blue and red, is we would shine, no one can be beyond the 6th row. I don't know where you guys are, but I don't care if you're late or whatever, you got to be in the 6th row or forward. Come on up. All right? One of the things we did is we wanted to confirm that mussels behave on a daily basis, that they do things every day. And so what we did in that top experiment is we would shine light on the mussels and then turn the light off on kind of daily cycles. And what we did was we put a sensor on the mussels that could sense whether or not their gape was open or closed. So I say gape, it's like their mouth. All right, you got what I'm saying? So we put a sensor on the mussel that says, is it open or is it closed? And then we shine a light on and say, when the light is on, is it open or is it closed? And that's what that data is up on the top. So we can shine light on it, and when the light is on, the gape is essentially closed. When the light is off, the gape is open, which kind of indicates that mussels are nocturnal feeders. They like to do their business at night as far as when they feed, but we're trying to learn a little bit more about that. But the key is we confirm that they do behave on a daily basis just like you and I. They're doing things every day on some sort of a cycle. Here's what the mussels look like in our laboratory setup. We've got a few mussels in there. We're putting them at a density of about 40 mussels per square meter, which is a pretty typical density at a mussel bed that we're working at in the Mississippi River, and also one that we're working at just up here in Coralville, right by the Iowa River Power Restaurant. If you know where that is, right where the dam is. There's a nice mussel bed just downstream of the dam, and we're doing some work there too. And that's where these mussels came from. These mussels that we use in our lab are called pocketbooks and three ridge, amazingly named. The three ridge has 3 ridges on its shell, pretty creatively named. The pocketbook is very large. Some of these mussels are very big. They fit in the palm of your hand. Other mussels that we might work with, like a Higgins eye, are very small. There are a variety of species that are indigenous to Iowa that are pretty interesting. One of my favorite named mussels is called a heel splitter, because if you're wading out in the water barefoot, it'll split your heel wide open. This is what our laboratory setup looks like. We've got 6 different acrylic tanks. 4 of the tanks have mussels in them, and 2 of the tanks do not have mussels, because we want to be able to discern what happens when there are mussels versus when there aren't mussels, and be able to kind of quantify that. We also have those grow lights up there at the top. Those grow lights are solar simulators. They're really powerful mercury halide lamps that put out energy in what's the photosynthetically active range, it's called. So it's PAR light. And so it tries to simulate the sun as best we can. It's a little hard to do that in the lab. It costs a lot of money to do that if we wanted the real intensity of the sun. But we can do a pretty decent job here with those lights. Other things that we have here are very specialized and expensive sensors that can measure the water chemistry in these tanks, particularly with respect to nitrogen, on 30-minute time scales. And so we can measure nitrate, ammonia, chlorophyll as kind of a surrogate for phytoplankton growth, because all phytoplankton contains chlorophyll. We can measure total nitrogen, not in real time, but we have some surrogate measures for that. And so we can really measure this thing at highly time-resolved scales. So we can measure, again, these daily changes in behavior and water chemistry. All right? So one of the things we do is we want to model all this. So one of the things we want to be able to do as engineers and also as environmental scientists or whatever, we want to measure things in the lab, right? We're going to get all this data. Well, then we want to kind of compute that data. We want to be able to model it. We want to be able to say, okay, we know everything that's causing the data to move on a daily cycle. And then we want to put some beginning numbers in, and we want to then have a computer model follow that same behavior. The reason why we want to do that is we want to be able to predict what would happen at larger and larger scales. So we want to take what we learned from the lab as far as what mussels do with nitrogen and say, well, what would happen if we had X amount of mussels, at a certain density in the Iowa River? How much nitrogen can we process along that stretch of the river? If we had this many mussels in the Mississippi River, how much nitrogen could we process? And start doing some scenarios and predictive values. So we want to be able to quantify what these mussels are doing. And this is just a big schematic where, in a nutshell, what we want to do here is quantify ammonia, that's in that box, phytoplankton in another box, organic nitrogen, and then nitrate. Those are all the things that we want to watch in this system on a very daily basis. So if it's a box, that means it's called a stock, and we want to measure the mass inside that box, I guess figuratively over time. And so we're able to model that stuff. One of the things we want to do is show value of mussels with respect to nitrogen processing over time. All right? We want to say, hey, if you spend a lot of money and restore the river so that more mussels will grow there again, what nitrogen processing value will you get in return? And so what we've done here, it's a little bit, I can explain it as best I can. Here we go. So if you see, where's my legend? Okay, blue. Blue is nitrate. You see that up there? ... Control tank is nitrate. Mussel tank, solid blue, is a nitrate in a mussel tank. All right? And so blue data is going up, and see how it's moving on a daily cycle? See all that every single day? This is over several days, about 2.5 weeks or so of data. You can see nitrate on the blue line. Do you see it? Up and down every day, nitrate goes up and down. Why does it go up and down? You start the dialogue right here. Why do you think it goes up and down? Yep. I don't know. What do you think? Fluctuates, nitrate, it's up and down.
It's changing.
Okay, it's changing, but why? Okay? Mussels will excrete ammonia, not necessarily nitrate, though. Good thought.
Is it due to the water levels being different from day to day?
No, pretty much a steady water level in all those tanks.
I guess like trying to mimic like rainfall patterns and stuff, like how she showed us how different days were.
If it does rain, we will see that signal in our system overall, but rain won't cause that daily up and down of nitrate. Go ahead, Richard.
Did you say mussels are nocturnal and nitrogen supply during the day?
Possibly, but they don't eat nitrate directly.
Does sunlight play any role in the algae that creates?
Oh, we're getting so close. Yeah, you are on it. All right, so we have sunlight being simulated, 12 hours on, 12 hours off in this system. When the sunlight, the solar simulator is on, phytoplankton starts to grow. Phytoplankton grows. When they grow, they take up nitrate, just like any other plant, right? You put some fertilizer on your yard. That's typically, it can be in a reduced form of nitrate as well, or of nitrogen. So then you'll start to see as phytoplankton grows, nitrate will go down. So phytoplankton up, nitrate down. But anyway, we can see that go up and down. All right, good job, you guys. Well done. So nitrate's moving up and down over time. Ammonia is the green. Ammonia also moves up and down over time, but it's kind of hard to see. It's the reverse of nitrate. You see ammonia's going down, nitrate's going up, right? So, and that makes sense, right? Because they're just kind of the opposite of each other in a way. One's reduced, one's oxidized. They're going up and down, but kind of on a reverse cycle. And the ammonia goes up during the night when mussels are pooping and peeing. All right? So that's when the ammonia goes up at night when the mussels are pooping and peeing. Also when the phytoplankton isn't growing. And also a lot of times the phytoplankton is decaying at night. As it decays, ammonia comes out. All right. Then we drew these lines through here. All right? Dot, dot, dot line means a tank that has no mussels in it. And we can say that nitrate goes down 0.02 or 0.012 per day in a tank with no mussels. And it goes down 0.018 per day in a tank with mussels. So that essentially means the ecosystem value with respect to removing nitrate from the water column attributed to these mussels is the difference between 0.018 and 0.012. So 0.006 per day can be attributed to the value of the mussels to remove nitrate. Make sense? So then we can try, we got to do a little more work with this. This isn't final. But then we can try to put a value on X number of mussels to remove X mass of nitrate in the river before it gets down to the Gulf of Mexico. That's kind of where my research is going. The last thing I'll show you is I told you we wanted to model this as best we could. So the dots are what we measured in the mussel tank. The black line up there is, we're doing phytoplankton here at the moment. So the black line way up at the top is a control tank with no mussels, and we're looking at phytoplankton going up and down on a daily cycle. The dots are the real data. For phytoplankton, we're actually measuring chlorophyll. We can't measure phytoplankton directly. We can only measure the pigment in phytoplankton directly. That's the chlorophyll. We can measure that in real time. And the dots go up and down, and then that solid black line is our model. That means that we're able to predict that pretty well. Down below here, the green ones, that's the exact same thing, phytoplankton, but in a tank containing mussels. And again, we can model that almost ridiculously well. I don't believe this, in fact. One of the things about modeling, you have to be very critical of what your models kind of tell you and what they might not tell you. You can be tricky with models and turn a couple values in such a way that it almost gets too good. And so right now we're at that point where we're being very skeptical about this data and this model and trying to say, hey, does this really make sense? And being very critical thinkers about it. But you can see where we're going, all right? Does that make sense? So the point of all this is, in addition to what Mary described as ways to mitigate, the ways to fix the problem, once it's already in the river, right? The river can actually take care of some of this problem as well. Obviously, it'd be better just to not get all the nutrients in the river in the first place. But as part of an overall solution to this issue, or with what Mary described as a way, knowing that we're going to keep tilling the land, and that's going to create natural occurring nitrate and different things that are going to run off anyway, even if we reduce the amount of inputs we put on the land, we still need to mitigate that, right? That's still going to get into the river. This might be one way to do it in the end. So I'm going to stop there and make sure we got lots of time for interaction and questions and whatnot, because that's my favorite part, if you couldn't already tell. All right?
I think this is a very interesting sort of departure for us, because it's a very sort of scientific approach to making good policy. And maybe I'll just kick things off, because I wanted to ask this while Craig was talking. So you have these tanks. How do you control for the fact that in a river, as opposed to a tank, there's a lot of other stuff going on? I mean, there's fish and debris on the bottom, and how do you account for the differences in the control environment and the real environment?
And we can compare and contrast how our tanks deal with that water. The nice thing about it is that these mussels need all sorts of hidden, unknown things to really be healthy for long periods of time in these lab environments. And so you can't do that with a reductionist approach. They're just not healthy. So the fact that I've got a pregnant mussel that's displaying her, kind of reproductive organs means that these mussels are quite healthy. This mussel, that pregnant mussel, has been in the tank for about 2.5 months. That's a long time to hold a mussel kind of in captivity, I guess, in that sense. So to answer your question,
we don't have every element that's out there in the river in our system, but we have way more elements than anyone else has done. And so that's where I'm trying to position my research as a way to kind of compare and contrast on a more holistic system than what has been done in the past. So we're not there yet. So I do want to go get a fish and put in that tank where that pregnant mussel is to see if she'll inject her larvae into that thing. I got to tell you that, but I'm not going to do it. It's not what we're about. But yeah, go ahead.
With whole fish and mussel interaction, what happens to the fish afterwards? Like, I know you said there's scales, like it goes to the
On their gills. It doesn't hurt the fish at all. Yeah, because the juveniles are really, really small, and I don't even think they're on the gills for even a year. And actually, mussels are pretty interesting if you ever see them. They're like tree rings. You can actually, kind of estimate how old they are. You can almost count their rings as they get larger and larger and larger each year. But the juveniles are really small, I don't even know, like the size of a little bit bigger than a pea. And they're not very big. And so they're just on that gill for a while, and then they fall off, and the fish is fine. It doesn't hurt the fish. That's great. Dive in, yeah.
So what happens if you guys, say the mussels theory works and you go ahead and implement it? What happens if they overpopulate, just like how we've tried using other to fix other problems that happen? I mean, when you say keel splitting mussel,
They're natural. Sure. So there's already some case studies of that where invasive mussels called zebra mussels have already populated, like the Great Lakes in particular, and they've totally turned the ecosystem upside down. Because zebra mussels, they're very tiny, but they reproduce extremely fast, and so the overall biomass in a zebra mussel in the overall population is huge, and they filter millions of gallons of water. And so they essentially strip the water column of phytoplankton. And the phytoplankton is essentially the food that then feeds zooplankton, that feeds increasingly larger organisms, that feeds small fish. Then the small fish get eaten by the next bigger fish, and then these nice game fish like bass and other things that you might want to catch, they don't have food anymore. And so you have to be careful of that. And that's why, even with Mary's perspective of what Iowa, used to look like landscape-wise hundreds of years ago, we also know what mussels look like and what their populations were hundreds of years ago as well. And so we're really we'll never be able to go back to that, and we'll never be able to go back to just Iowa as a prairie. So we're trying to figure out how can we, as human engineers, engineering this ecosystem, how can we get some of that functionality back that used to be there before, but still have some of the things that we might want otherwise, with respect to industrial ag, essentially, and how can we keep them going. So we have to be careful of that. But we do know what species to put in, but it's going to be it'll be expensive to do. It's going to cost a lot. I'm guessing more than it'll cost to do a wetland. We're doing some of those calculations now to figure out what that would cost. But so I don't know who's next. I think you do you have a question? Yeah, be brave. You bet.
I guess, do we know why the mussels kind of disappeared?
So go back to one of Mary's slides. Do you remember she listed several things on why our waters are impaired, and it was the third bar on her slide. The first one was nitrate, if I remember right. The second one was pH. Anybody remember the third one? The third bar on her slide? Free slice of pizza at Mesa. Anybody? Serious?
Macaroni and cheese?
I love macaroni and cheese at Mesa. Anybody? It was sediment. So we're essentially burying the mussels alive with sediment. So, with our erosion due to row cropping, essentially, that sediment gets delivered to the river and just chokes out these mussel habitats. If you look at the mussel bed that's near Buffalo, Iowa, on the Mississippi River in what's called Pool 16, because there's locks and dams on the river, so there's essentially pools in the river. There are really nifty mussels, the more desirable mussels in that mussel bed at a higher density overall in areas where it's essentially like walking on large pebbles. And then there's another part of the bed where it's all muddy and murky. There are still mussels there, a lot less, a lot fewer of them, and not what we would call the desirable ones. They're kind of the more murky one. Unfortunately, we discriminate against mussels. We like certain ones and don't like others. And so we're essentially choking them with sediment.
Can I add to that?
Yeah.
So one of the things that if you look at some of the historical documents, the Iowa mussel beds were harvested extensively for button factories. There's pictures in the Muscatine area around the Mississippi River, huge areas that would fill this room of mussel shells that were used to basically make buttons. And so one of the things you talked about the long life, you have to have that fish host. So you start to have fewer and fewer mussels. So you got to find the right fish host with the pregnant mussel at the right time, and then find the right habitat. You start to really make a challenge for that thing to actually reproduce effectively. In addition to having dams being built on the rivers, so now we've created fish barriers where the fish can't actually find the right, the right mussel and then move those mussels around. So there's a number of factors that start to really look at, it's sediment and it's dams and it's other chemicals as well. And so it's sort of, the odds start to really go down that they can actually reproduce effectively. Where they have been sort of helped along with reproduction and introduced, they've done fairly well.
Mm-hmm.
But you have to think about all these other things that we're doing to the ecosystem.
I just want to, Mary, can you talk a little bit, because I always try and get the history in here, talk a little bit about the stream straightening as well, as a
Sure.
consequences?
Yeah, I mean, one of the things that we've done is, in order to reduce flooding, a lot of times what we do is come in and straighten the stream, because straighten the stream, that water will move away a lot more rapidly. So we take a sinuous curve and we cut a straight line through that, and the water really moves fast. We entrench that stream, so we have banks that look like this now instead of gentle banks. And all that velocity, just rips on the banks. It creates a really inhospitable environment for the mussels because they can't handle a bottom that's always moving and with huge volumes of water coming through. So every time we straighten that, we increase the power of that stream, which is completely overwhelming for the mussels and delivers a lot of sediment and other things very rapidly into the stream. So, we've really changed the power of the stream. It's constantly eating away at the banks and the bed.
Are cover crops harvestable? Like, can they make money off of doing that? Or is that something they would just kind of plant, not gain anything out of it?
Right now, they're not harvesting those, but it's obvious that we want to have a cover crop that's actually going to give you some money. So right now, they're planting rye and burning off that rye with 2,4-D in the spring. But I think we're not far off before people are going to start to look at what can we actually plant to get that second harvest. There's some concern that rye and some of these crops will go together well, so you might get some interferences between the rye crop and a corn crop. But I think, the benefits that we're seeing is that, if you could get a second crop for a farmer, I think we're going to start to see people adopt it, because right now, you put the cover crop on, you can get some subsidy to do that, but, without it being another crop, why would you do it? So we're just on that cusp of making it a profitable second crop, but I don't think anybody's really harvesting it yet there, other than possibly some people for their cattle or something like that, but it's really not happening yet. But it should.
As a follow-up to that, we've done research in our group with hybrid poplar trees and planting them along the stream banks to stabilize the bank, number one, because they're very deep-rooting trees. They grow very rapidly, but then they also take up nitrogen along the way. Another interesting thing about hybrid poplar trees is that if you cut them off, they'll grow back from a cut stump. So you don't have to till the land or do anything to harvest that woody biomass and then have another crop grow right on that. And so one of the things that we've done recently this past fall, they did a test burn in the University of Iowa power plant. We have some coal-fired stoker boilers, but we also have some boilers that have been modified to be able to take in biomass. And we did a test burn of poplar trees. One of the things they're concerned about, though, is that they are nitrogen-containing, and that will put out, I don't know if you guys have done any policy work on NOx and SOx, but NOx is a nitrogen-containing kind of smog, nitrous oxide and different things that you can then put out the smokestack. And it causes smog, and so there's an impact of burning a high nitrogen-containing woody biomass. But one of the things we want to do in the MBA program, in fact, they've done a kind of a calculation on within a roughly 50-mile radius of the University of Iowa, how much woody crop would it take to power the power plant. And so one of the things you can imagine is then a cash crop in woody biomass, not corn or soybeans, that would be planted in a way that wouldn't disturb the soils very near those, the riparian, the buffer zones between the field and the stream. They don't help much when you've already tiled it, though. The nitrate still goes right under the trees, but there are some ways to still intercept that tile water with the trees. So that's another interesting thing we can try to look at, too, as a cash crop for farmers as an alternative to corn and soybeans. But it takes a pretty progressive farmer to do that because you're not going to make money in the beginning years as much as you would otherwise. So there's a conversion time. So I think you might have been next.
Can I just jump in there? I thought,
Sure.
One of the striking things I always thought in Connie Mutel's book was her description of the way in which, you initially have the displacement of the prairie grass and the sort of going, stream to fence row to fence row. But then you have another sort of dramatic change with the advent of the internal combustion engine.
Exactly, yeah.
Because you're no longer growing that silage crop for your animals, and you can do corn and soy exclusively, and that has another sort of quantum leap in the way in which the soil was degraded.
Yeah, and really, even if you go back even 30 or 40 years, we've lost small grains, we've lost alfalfa, we used to have some oats, we've lost that. We've become so corn and soybeans heavy that even those other small grain crops used to provide some of the function that some of the grasses did. Not quite as well as the prairie grass, but having some diversity is really helpful. One of the things that we're very concerned about is that we're robbing the organic matter of those soils, which leads to a variety of problems, not only the nitrate, but they become like concrete. So for example, the flood of 2008, you have soils that simply can't infiltrate water either because they're saturated or because they're so dense, they're so clay-rich, you just simply can't get water through them. And a lot of that's the loss of organic matter that's just been slowly leached over the last 100 years. And so things that we can do like a cover crop are going to build that organic matter back. And especially if energy prices remain high and synthetic fertilizer becomes more and more expensive, we're going to wish we had organic matter in our soils because we're going to need it to offset the, synthetic fertilizers. Yeah,
Go ahead, right here.
But in Iowa State report came out that you increase more sediment, like the last 30 years, I think, in our streams. And so sediment loads killing off mussels and then churning into the soil is just spewing more nitrogen out. What about no-till? How do you...
Go ahead.
Yeah,
Would that solve a lot of problems, or is it...
Yeah, no-till is a good solution, and it's one of those things that I talk to my agronomic friends a lot about. We've known the benefits from no-till for a long time, and we have remained at about 25% of the cropland in no-till. It's one of those challenges that they're not sure how to convince more producers to go to that direction. There's a certain amount of, it's almost culture that people, either they were taught that this is the way that they should do it, and changing that culture is difficult. Now, some of it is also equipment. So if you have certain types of equipment right now, buying no-till equipment is going to be an outlay of expense that you have to put out there. But it just seems like we can't get over that 25% or 30% hump because people just don't think that it's the right thing to do. And there's a lot of mythology that comes in there. They want dry soils. No-till soils don't dry out as quickly. So when we've had 2008, 2009, 2010, we've got these wet springs, people are very superstitious about if I don't have dry soils, when I'm ready to go in April, I'm not going to get my crop in. And so there's a number of these sort of society issues that start to intervene about, okay, how do we take some of that risk away if you can't get your crop in because the soils are a little bit wetter? Or can we come up with varietals that can handle having a wet soil? How do we offset the cost of that equipment? How do we incentivize going to no-till? Because we know the benefits. And so it's more than just a pure science, it's the right thing to do. It's all this other society stuff that we can't quite get people to buy in. And I think it's the right combination of incentives. So that's a big challenge for us.
Oh, I don't even know what to do. Yeah, how about you in the back?
Government subsidizes the growth of corn and soybeans. Do you think it'd be more effective to subsidize like the power plant, actually like farmers to actually not plant anything for a year or two?
There have been programs like that. There was the Payment in Kind program, which basically did some of that fallow land subsidying. Right now we're in this kind of strange situation where for the first time corn prices are so high that the subsidies aren't really, again, providing much incentive for producers. So with these high corn prices, people are taking out grasslands. They're taking out, there's a CRP, which is Conservation Reserve Program. You enroll your highly erodible land into grasses or you put in trees. People are pulling those contracts early. They're paying the penalty to do that to get in on $7, $8 corn. So it's really challenging when you look at the rent for a CRP piece of ground for a landowner. I can rent to you, you're going to put in CRP, you're going to pay half or a third of what someone who's going to rent that for a corn crop is going to give me. So there's all these incentives where the government would really have to pay big money to put in fallow. And again, having worked with a number of producers, there is this Iowa work ethic about fallow land is seen as almost sinful. Mm-hmm. That land should be put in production. I know a good friend of mine has a wetland, and her dad is very concerned about that land is just sitting there. Should be doing something. So there's this culture of, well, it is doing something. It's providing an ecological service. It's not working in the classical sense. So I think the combination of not being able to pay enough and then overcoming that sense of, why aren't you working that piece of ground over there? I could pay you rent and we could get a corn crop off that, and that would be a societal benefit. Changing that mindset's very challenging. The last thing I'll throw out there is if you look at Iowa, it's aging. And many of the landowners are absentee. They're living in Arizona, out of state. A lot of their information that they get is through their renters. So they're talking to the renters about, well, what are you going to do? And the renter's saying, well, I'm going to do this on the piece of property. And so we need to work more extensively with those absentee landowners about, you should require a certain level of conservation before you rent that piece of property. Because right now, everybody wants to rent that property. You're in the driver's seat. You should require that. But it's a very big challenge when you've got an 80-year-old lady sitting somewhere far away who doesn't know what her, what she could be doing with that property.
Mm-hmm. Okay, go ahead.
Okay, so with ag practice and policies, how important is sort of carrot versus stick measures and making these things happen in terms of like maybe political will to make those things happen, and since the issue you're talking about with farmers making changes?
Yeah, carrot or stick, and with the DNR, I don't do any regulation. That's always my first disclaimer. I wear the white hat all the time. But I guess I believe in that both are necessary. It's great to incentivize, to say we want to pay for practices, to incentivize you to do the right thing. The problem is that there are always going to be people that don't want to follow that. And having the stick does allow you to bring all the bad actors up to some minimum level of standard. I think it's necessary, partly because some people they're not coming in to get their conservation plans done. They simply want to just do what they want to do, and the stick helps to bring those folks along in a way that, like I said, is a minimum playing field. Because if I want to be a good actor and do the right things, but I'm taking a financial hit to do that, then there's sort of that, well, why don't I just not do anything at all? So I think they're both valuable. Much like I don't want to get stopped by a trooper for speeding, too quickly. But look at the S curves in Cedar Rapids. The number of accidents because of the traffic cameras have dropped significantly. The average rate of speed has dropped. People didn't do that out of the goodness of their heart or because they didn't want to die on the S curves. They did it because they knew somebody was there enforcing that. So I think you have to have both just to keep everyone on the up and up.
Wow. Don't even know where to go. No. I just like all these hands on up. Why don't you go? Okay.
Kind of going off of her question, so do you think that these, like the carrot or the stick, do you think it should be implemented more as like a state or local or state or national government, or do you think that it should be more of a local choice based on the counties and the farmers in the area kind of make their own choices on what they want?
Yeah, so the question is, at what scale is that carrot and stick applied? I guess I believe in, for example, the Clean Water Act, I think, is a pretty good way of doing it. the federal government sets sort of minimum standards again. So under the Clean Water Act, the EPA is going to say, we think the nitrogen standard should be this, or we think you should regulate in this way. And as a state, we have an option to be more strict, but we can't be less strict. So for our local environment, if we wanted to really try and preserve the mussels or do something, setting that bar at the federal level, setting the bar then at the state level, should, I think, allow the local folks to become more strict or customize the stick at a local level, partly because when you have to look your neighbor in the eye, you're, again, more accountable to that person, your neighbors, about, I want to protect the water quality, I want to do the right things, and I think local watershed action is where it's really going to happen. But having those backstops that say, at a very minimum, you have to at least meet this, I think everybody can agree that that needs to happen. It's just, so what is that minimum? But I think it works well to say, well, okay, at least Illinois, Iowa, Kansas, we're all here, but maybe we want to be a little bit, if we're concerned about the Iowa River, we want to go a little bit further, and we want to work together to make that a better place. So.
Yeah, and as a follow-up to that, one of the things that, water doesn't follow jurisdictional boundaries, right? So, and Mary mentioned watershed approaches, and, there's some different watershed associations, I think, that are great, that can talk about things like that. One of the things that's really interesting to me are some folks way up in Iowa Falls, Iowa, up in that part of the watershed, in the Iowa River watershed. I'm kind of from that part of the world. They're doing the row cropping up in that Des Moines lobe that is highly erodible, and what was the word you had for that? Was the hydric soils that are well drained. But then that water makes its way down here and runs right through our campus. And so if we want the water here to not be green and brown, then one of the things we might want to do, especially as a part of the state that is economically thriving relative to that part of the state, would be then we would have kind of like a nitrogen and phosphorus cap and trade or whatever, a system within the watershed where people down here who want the benefits of clean water running through our campus, we would help pay for best management practices up there, because that's where it's got to happen. There's nothing we can do down here. It's too late as far as putting in filters or something in the Iowa River. And so I think it'd be interesting, too, to have, I guess it wouldn't be taxing authority, but have some sort of a jurisdiction that follows the watershed, so you could pass a policy based on that boundary, not a county or a state or whatever. Then you can really do something as a watershed group to make an impact. And I think that would be a neat way to do policy. Kind of challenging, though. People don't think in those terms at all. We just don't do it.
And even more challenging because sometimes it's an international problem.
Mm-hmm.
I mean, there's a joint commission on the Great Lakes that's supposed to deal with problems across the northern border, but there's a number of issues like the Asian carp coming up the Chicago River, or the falling levels of Lake Superior and Lake Huron because of erosion in the Detroit River that are almost unresolvable because there's no really credible political authority other than a sort of toothless commission.
Yeah.
Absolutely.
Go ahead. How about you in the white?
Some of the articles for today we talked about the limited funding for water control. So with the funding that is available, should that be, I guess, more focused towards waters that are already severely contaminated, or towards the ones that are like at a more lower and moderate level?
That is such a good question. Again, just to recap, it's where should we focus? Should we focus on the worst of the worst, or the ones that are savable? And boy, that is a great question, because sometimes, and I must admit, sometimes I go back and forth. Like, you want to go after the worst problem, but at the same time, you want to know that you can be successful. And we've got really high-quality waters, but we don't want to see them degrade. So in Iowa, we have what's called outstanding Iowa waters. They're considered almost pristine, but certainly very high quality. We want to make sure that they don't fall into a bad category. They don't start to degrade. So we should put some money there. There was a study that was done looking at Iowa lakes, sort of ranking the worst quality lakes and then how much money we're getting from recreation of those lakes. And what they decided is we wanted to focus on the in-between ones, that they were salvageable for water quality, and in doing so we would have the biggest amount of economic benefit from doing that, because we can put a lot of money into the low quality ones, but maybe we're not going to get any economic benefit because they're so bad. That being said, it's like all politics are local. If you tell somebody we're not going to worry about your lake or your stream, it doesn't go over very well, because everyone feels attached to their local water bodies. They feel attached to their counties. So it's really hard to prioritize. It seems so easy. It seems very logical. But when you really get down to saying, I'm sorry, there's no money for you, people get mad. They don't want to see that happen. So it's a really tough question. It's really hard to do.
We better go over here. I don't think we, how about you in the red maybe, yeah.
Do you know about any of the other policies that the other states who produce a lot of nitrate into the Cedar River are pursuing, how successful they are, and how big they go?
I don't know about policy much. You talked about Minnesota a little bit in your talk, but I don't know if that was a policy.
Yeah.
North Carolina.
Some states are a lot more successful. For example, Illinois is getting into that controlled drainage thing pretty heavily. For them, it's a little bit easier. We think Iowa's flat, but Illinois is even flatter. One of the challenges with controlled water drainage, if you're going to stop up that tile line, that water, backing that water up can blow out your tile line. So you have to do it carefully, and if you've got a lot of slope, you have to put in more check structures. So it hasn't quite been as easy to adopt in Iowa, where we're actually not as flat as Illinois. So Illinois has been doing that. Part of the problem with Iowa is because we don't have a significant urban contribution for nitrate, it's harder to get urban populations to get on board. In Illinois, you have Chicago, and Chicago is a significant contribution to the nitrate problem in Illinois. So you can kind of bring rural and urban together in a way that I think is effective. Oftentimes the urban voice is lacking in Iowa for some of these issues. Minnesota, I think, has been pretty effective in policies, wetland restoration, wetland protection. Other states like Kansas tried to go a route where they said, we're just not going to protect any, basically we're going to take water quality standards off all of our water bodies. Deal with that, EPA. So you kind of have the gamut of people that want to walk away and others that have been, I think, a little bit more proactive, and we're somewhere in the middle, I think.
And I'll say too, the Army Corps of Engineers, I work with those folks quite a lot, and they are very keen on doing habitat restoration up and down the Mississippi in particular, and that transcends a lot of different jurisdictions as well. And so they have to do navigational maintenance, so barges and ship traffic can get up and down, but they also are charged with bringing back some of the ecosystem functions that have essentially been engineered out of that system, and they're doing it in really smart ways, I feel, and they've got money to do that as well. So that's kind of not a state or whatever, but it's a national, kind of a federal level agency that at least is trying to enhance their mission with keeping the environment in mind. Yeah, in the blue, I guess.
How is this being received politically, as far as, because we have a Republican governor and supports Republicans have always been less regulation. Just wondering how, politically speaking, how it's received here in Iowa.
The muscle piece or the water quality piece in general? In general?
Maybe more so.
It'd be the nitrogen piece, yeah.
So it's interesting. I think that classically there has been this division, red-blue, for environment. The lake study that I referenced before was very interesting because people of both political persuasions could get around a report that said, if we invest in water quality, we will see an economic benefit. And that was pretty uniformly accepted across the political spectrum, that we ought to invest in that. And what happened is they invested about $9 million a year in lake restoration to start addressing those issues. We're seeing that Charles City, for example, took out a dam and they put in a whitewater park. They've had 1 million hits on their website globally for this little whitewater park in Charles City, Iowa, because people want to actually recreate in cool places. Now, I don't think Charles City is any cooler than anywhere else in Iowa. So people are starting to understand that quality of life, recreational opportunities is good for business, it's good for bringing people back to Iowa, it's good for keeping people in Iowa, and we're seeing a lot more support for that. Now, that being said, for a lot of people, all government is bad, all government spending is bad. So on one hand, they want to cut the spending, on the other hand, they want these things to happen. Sometimes it can happen with private donations, but sometimes it can't. And so there is a little bit of a schizophrenic kind of, on one hand they want to give, on the other hand take away. So it's certainly not a clear-cut thing, but the biggest battleground I will say right now is standards. Should we have a nutrient standard for the state of Iowa? We're approaching it right now as a voluntary strategy to reduce nutrients, being the agricultural groups coming together, developing a strategy, the point sources developing a strategy, and we'll see if we can handle it through a strategy as opposed to standards, and that's had some acceptance on both sides of the aisle. We'll see if it actually hangs together for the long term.
Do you want to say something about the proposal to move water quality?
Yeah, I mean, there have been a number of proposals. One is to move the water quality monitoring program out of DNR to the Department of Agriculture. Move the 319 program. EPA 319 provides a lot of those best management practice dollars that I showed you, things like wetlands and filter strips, goes to DNR right now. There was a proposal to move that out. I think there was enough of a disagreement from the public about that's not going to happen, but these things come up time and time again. We'll see where that goes long term, but for a long time the assumption was no data meant good news. We don't know, everything's fine. I think we have learned that no news is not good news, that we're ill prepared to handle the challenges of the future. When you have someone whose lake turns bright fluorescent green, they want answers. Well, we need to know what the water quality is to provide answers for how to make that lake not bright green. In the case of Clear Lake, it might be zebra mussels.
That's
so
right.
There's your solution. But we need to know, to actually know if we're spending the money the right way and how to solve these problems. So I think we're starting to not assume that the lack of information is actually a good thing. I think we're finally over that hump, and that DNR's done an okay job with the monitoring program so far, so why move it?
Go ahead.
What do the mussel takes take into account, like the flow of the river? Like you were saying, I guess I just want to know that.
So yeah, a mussel in a natural environment will orient its siphon facing upstream, so things are kind of coming at it, and its gape will be downstream, so that's the way it'll orient itself in a natural environment. We can't do a full flow regime. All we can do is mix. So we have these, they're essentially sump pumps, but they're small, like little fish tank aerators. They're bigger than you'd have in your fish tank, but they're totally submerged, and all they do is just kind of keep that water circulating in there. So we're kind of mimicking overall flow. What's most important is that we are able to keep their food suspended long enough for them to filter it. Because they can actively pull in. I mean, they got this muscular body, they can suck stuff in. They don't need the flow to eat. And so we don't have to fully mimic that, because mussels are in lakes and everywhere else too. We just happen to be studying, kind of ones that we're getting from the river. So the flow regime isn't all that necessary for our lab component.
I guess my question was because we haven't improved like you said, when we pull out curves, that's what's caused the mussel reduction. Are you trying to get to the point saying like we reintroduce these mussels, it will reduce the amount of nitrate in the water, or is that just kind of step one in what you're doing? We also know hydrodynamically, based on water flow, what mussels prefer. And we know that they don't like main channels, they don't like fast flow, they don't live there. They live in water of certain depths. The ones we're dealing with, are in 3 to 4 feet of water. And they don't like to get their habitat all, sediment laden. So we would know from a kind of a physical standpoint on how to create that habitat. We would then know also chemically from a nitrogen standpoint on, how to put the mussels in that habitat to get the ecosystem function we want with respect to that. By the way, I don't want to, most of the nitrogen in a river is removed by bacteria. Mussels are a component to this, but most of it's by bacteria, and they also have kind of a
a favored environment for where they'll actually reduce and get rid of nitrogen as well. So we're really trying to engineer for both of those systems and try to understand what the mussels. So really, in the no mussel tank, that means bacteria are in those control tanks in our lab, and then the other ones are mussels and bacteria. So we can kind of differentiate it that way. But yeah, we can, from the hydrodynamic standpoint, we can engineer for that as well, and then also get the chemical benefits we want after we make a habitat that they like. If that kind of makes any sense. Because yeah, they will pick where to live based on the physical environment. They don't care much how much nitrate's there. That's not really like their thing. So you're right, we have to design the habitats for what they'd like it in a more physical way. I don't know, maybe, yeah, Hawkeye guy.
You guys talk about recreation, how you want to bring people in lakes and rivers to build the economy and stuff. But what effects do those boaters have on mussels? Like still an awful lot of mussels.
What effect do boats have on mussels? Well, a couple of things happen. One of the first things that happens is boats move invasive mussels around a lot of times because they'll be stuck to their hulls and all, even like Eurasian milfoil and other plants that you don't want to move from lake to lake to lake. That's why when you pull your boat out, they like to have you wash it down and try to keep those invasive species in place. And so that would happen with mussels as well. The thing about the mussels is they're typically in the shallows, so I don't think the boats do a whole lot with them. I would say that the otters and muskrats and others, that's right. So if you go by the Iowa River Power Company and look at the shoreline there, at certain times of the year you'll see a whole bunch of empty mussel shells on the bank, and that's not from mussels marching uphill and killing themselves. It's from muskrats. It's from muskrats and other animals coming and eating them, and so that's their main predator, I guess. So the boats don't do a whole lot, to my knowledge.
Let me add something to that, at the risk of being the bleeding heart environmentalist. One of the things that we're concerned about is because they're in the shallows, ATVs have become increasingly popular in riding ATVs through creek beds, and you can do an awful lot of damage to a mussel bed just by riding an ATV through there. So, and there's not a lot of people watching to make sure that isn't happening. And so, and again, I don't want to blame those folks because they probably have no idea what's in there, but it can do an awful lot of damage if you take an ATV backing up and through some of those areas. So it's about greater awareness that there's maybe better places to do that activity than up and around in the creek beds.
So instead of a heel splitter, we need a wheel splitter, I guess, right? Get rid of those ATVs.
Well, I mean, the other piece of that would be, and we touched on this, that much of the recreational boating area in Iowa is created by low-head dams, which back up and slow down and warm up the river. Mm-hmm. So that reduces the habitat. It's not the boats themselves, but the creation of the area to go boating that changes the equation.
Yeah, absolutely.
Well, it seems like this issue is kind of a classic example of tragedy of the commons. A lot of people who need agriculture to make money. So since there's not an easy way to sell them from or see that it's just important to conserve the land, they just want to use it so they make enough money. But there have been certain solutions to tragedy of the commons. One with privatization. Obviously, I just don't think it's worked, just because what incentive does one farmer have to really make changes, even though all of his neighbors are not free riders. But another one would be to actually try to ration how much nitrates and how much other fertilizers and pesticides. So if there was a dominant beneficiary to actually oversee and take control of this, should this be more of a regional cross-state kind of cooperation, or should this be more of a one company actually sort of solving the problems and then sort of trading the reductions in nitrogen for to keep that going? Like a market solution.
That all sounds really complicated. But I know where you're going. So first of all, I think the jurisdiction is the watershed. Otherwise, it's not going to do you much good overall, because you're going to have to move within the watershed around. You mean you're going to want to move those pieces strategically, and that's really the only way that those benefits are going to come together. And then obviously you can link watersheds together to then solve the Gulf of Hypoxia sort of an issue. That's for sure. But it seems like watersheds that I don't even know if you can get much bigger than like you guys might not know your Huck units, but like a Huck 8 seems, that's like the upper Iowa and lower Iowa. So I don't know how many Huck 8s would there be in Iowa. Maybe about 56 Huck 8s. So if you divided Iowa into 56 watersheds, those seem like sizes that people can manage. So with 56, they're not that much larger than counties. And people kind of have that familiarity with that. It seems like, if you could get some jurisdictions like that, you might be able to start approaching that. And then a few of those would then link together, which would be a Huck 6 and a Huck, increasingly larger watersheds as you had some success. But it's just amazingly complicated because none of our money flows based on watersheds, no pun intended. But
and let me add something to that. There's a new thing that's starting to develop in Iowa, which is called a watershed management authority. Minnesota has watershed management districts that have actually taxing authority, and they can do all kinds of things. We're seeing the emergence of these watershed management authorities that came out of the floods of 2008. There's some money available. One of the things I think that's going to happen is we can't just focus on nitrate. What I was attempting to do is to talk a little bit about it's the hydrology, it's the water. So we need to think about how do we manage our water to prevent floods when we need it in the case of drought, to hold back sediment, nitrate, all these other things. So it's about managing that water in a whole different way, and I think that those management authorities have the possibility of saying, how do we look at the multiple benefits and the multiple issues at once so that we're not flooding Cedar Rapids, that we're not having too much nitrate coming down the stream in a way that makes sense. We've had a lot of flooding over the last couple of years, very dry right now, and so we could very easily shift into a couple of years of drought. People are going to want that water. How are we managing that water in a way across these boundaries in a logical kind of fashion? And I think those management authorities have real potential, and they've worked in Minnesota. They're being fairly successful to get things accomplished in Minnesota. So stay tuned on that. It's a new experiment for us. Because it doesn't have taxing authority, it may not be as successful. But that's a new way of thinking about organization for a variety of problems. Can I say one last thing?
Yeah. I
have to put in my plug, my advertisement. It's important for you all to get involved. I understand that you're in a class or here tonight to hear some stuff, but the future is yours. Craig and I are getting old. The future is yours, and I really encourage you to get involved. We have a volunteer monitoring program. You can get trained to start sampling, understanding your local water bodies. It's called iWater. I encourage you to get involved because until you actually get in the stream, start looking at the stream in a whole new way, you won't really start to understand the problems that are out there. And it gets neighbors talking to neighbors and communities talking to communities. There's river cleanups. I really encourage you to get involved. It's going to be the solution, ultimately coming from you all, not from agencies. So that's my plug. Get involved.
Do you want to mention AWARE?
Sure. So Project AWARE is a 7-day, 7-night canoe trip where we pick up garbage along a river. This year we will be on the upper stretch of the Iowa in the Iowa Falls area. It's July 7th through the 14th. All you have to have is a desire to do something. We provide canoes. You can get catered meals. It's camping. You can come 1 day. You can come 7 days. This is our 10th year. Your professor has been coming many years. It's a great event, and you really start to understand how you can make a difference neighbor to neighbor, sitting in a canoe. We've had producers looking at banks sloughing off. Hey, why is that bank sloughing off into the stream? Well, did you notice the corn row is sitting right on the edge of the stream? What if we back that up? How can we work together? So it's a great event. We've pulled out tons and tons of trash, and I encourage you to check it out. www.iowaprojectaware.com. Find all about it. So definitely looking for strong backs and arms to come help pull trash out.
If you've never taken a refrigerator full of sand out of the middle of a river and tried to put it in a canoe,
You will never throw a pop bottle away ever again after you have scrambled out onto a log jam to get that one Mountain Dew bottle that somebody just kind of tossed away, and you're out there trying to get that thing. You won't ever think about just throwing that baby away ever again. So it's hard, but it's fun. So check it out.
Okay, well, let's thank our guests one more time.